Okay, so welcome to Expectation Values Part 8. So this is again going to show you a problem that uses linearity of expectation values to solve. Okay, so this problem comes from the Putnam exam. Here's the problem. You have n digits. So 1 all the way to 3 all the way up to n. And you can permute these around, so you can order them in different ways. So for instance, let n equal 6, then you have 1, 2, 3, 4, 5, 6. A different permutation would be 2, 1, 3, 4, 6, 5. You could permute, and there are many different permutations. So for instance, in the first position you can put 6 different things, in the second position you can put 5 different things, in the third position you can put 4, and so on, and therefore the total number of permutations is 6 factorial. In the more general case, the total number of permutations is n factorial. So you can permute them around, and basically what you want to do, if this is the starting point for this problem is that our probability space, our sample space rather, contains every single one of these permutations. So we put all of these permutations, all n factorial permutations, into this sample space, which we'll call omega. Okay, and each permutation is equally likely as far as it occurring is concerned. Now, we're going to set up a random variable which we'll call x, which is going to ascribe to each outcome a number, and the number it's going to ascribe, x is going to take an outcome and it's going to map the set of all outcomes onto the real numbers, and the way it's going to work is that it's going to count how many local maxima there are. So it's going to map x onto the number of local maxima. And the meaning of local maxima is that if you look at this and you look at each number in turn, you look at 1 and you ask, is it bigger than its neighbours? So 1 is not bigger than 2. 2 is its neighbour here, so 1 is not a local maximum. 2, you look at now the number in the second position, and again you look at both of its neighbours. It's got 2 neighbours, and it's not bigger than both of them because 3 is bigger here. Then you go to the third position and you continue on. Now the only one that is a local maximum here is 6, because 6 is bigger than its neighbour. It's only got one neighbour, but it is bigger than its neighbour. So the number of local maxima for this permutation would be 1. For this one you might have more. So for instance 2 here is a local maxima because it's bigger than 1. 1 is not, because 2 and 3 are both bigger than it. 3 is not because 4 is bigger than it. 4 has 3 and 6 as its neighbours, so it's not a local maxima. 6 is obviously a local maxima because it's bigger than 4 and 5. And 5 is not a local maxima because it's not bigger than 6. So this random variable would map that onto 2. So what we're asking, the question is find E of x, basically. Find the expectation value of x. Find what the expected value of local maxima is. Okay, the way that we're going to tackle this problem, again, as we've seen in previous videos, is what we're going to do is we're going to split x into the sum of lots of other random variables, and then what we're going to say is that the expected value of x is equal to the expected value of all of them added together, and those expected values of those smaller problems is going to be easier to find. So let's define x1 to map the sample space onto it's only going to map it onto the positive integers, because you can only have 0, 1, 2, etc. So let's just say the integers. Let's map x1 onto the x1 is going to map the sample space onto the integers, and it's going to map a specific outcome onto either. It's going to map it either onto. Oh, it's actually simpler than that. We're going to map it onto the Bernoulli space, so it's going to map onto 0 or 1. So we're going to map S onto, specifically we're going to map it onto 0 if position 1 has a local maximum, and we're going to map it onto 1 if, we're going to map it onto 0 onto a 1 if position 1 has a local maximum, and 0 if position 1 does not have a local maximum. Position 1 doesn't have a local maximum. So for every single permutation in this sample space, you can say whether or not position 1 has a local maximum, and if it does have a local maximum, then x1 will map it onto 1, and if it doesn't have a local maximum, then x1 will map that permutation onto 0. Okay, so that's all good. And now we can define some more random variables. We can define all the way up to xn, which is going to map any outcome s onto 0 if nth position is not a local maximum. Is not a local maximum, and it's going to map 1. It's going to map it onto 1 if nth position is a local maximum. So, for instance, this first permutation up here, nth position is a local maximum. Okay, so for instance, this first permutation up here, this 1, 2, 3, 4, 5, 6, position 6 was a local maximum, so this would be mapped onto, by x6, it would be mapped onto 1, and by all the previous ones, x1 up through x5, so we go along, there are loads in between here, x1 to x5, it would all have been mapped onto 0, or this permutation would have been mapped onto 0. Okay, so note that x is equal to the sum x1 plus all the way through to xn, because x counts the number of local maximum in the overall in the permutation, and if you add up x1 to xn, x1 is either 0 if the first position is not a local maximum, and it's 1 if it is a local maximum. So all of the so if you add this up, it's going to count how many local maximum you have, because if these are 1, then it means that that position was a local maximum, so each position that is a local maximum is going to get counted one time. Okay, so we now know that this variable x, this random variable x, can be expressed as this sum of these other random variables, and so we can say that the expected value of x is, by linearity, is the expected value of x1 all the way through to plus the expected value of xn. Okay, so if we can work out the expected value of each of these random variables, then we know the expected value of the overall random variable. So, there are two basic cases in this. There are firstly the endpoints, which are going to be different from the middle points. The reason being that the endpoints only have one neighbour and all the middle points have two neighbours. So, x1 is Bernoulli distributed, so we know that all of them are Bernoulli distributed, so we know that the expectation value of xi is just going to be equal to the probability of success, but the probability of success is going to be different in x1 and xn, the two end ones, than the intermediate ones between there. Okay, so the expected value of xi is just the probability of success of that position being a local maximum, Okay, so not onto that. Let's work out then these expected values. So for the first random variable x1, we are mapping our abstract probability space onto the Bernoulli space, which contains 0 and 1, and we're mapping it onto 1 if the first position is a local maximum, and we're mapping it onto 0 if it's not a local maximum. So what is the probability that we map it onto 1? Well, that's the probability that the first entry is a local maximum. Okay, so if you think about the n things, so let's draw out an example again. 1, 2, 3, 4, 5, 6. If you think about this here, we want to know whether this is a local maximum. Well, we're only comparing it with its single neighbour here. So it has a neighbour. Let's say these two numbers are now set. Either it's in the wrong order, i.e. this one is less than this one, or this one is either it can be in this order here, where this one is its neighbour is greater than it, or you can have them in the other order, 2, 1, where its neighbour is not greater than it. So the probability of it being greater than its neighbour is a half, and the probability of its neighbour being greater than it is also a half. So in this case, the probability that the first one is a local maximum is a half, and the probability of it not being a local maximum is a half as well, because you're equally likely it's equally likely that the first position is greater than its one neighbour, and it's equally likely that it's bigger than its neighbour as it is that it's not bigger than its neighbour. Okay, so now that's the same argument applies for xn. So in that case, the expected value of x1 is equal to the probability of success, i.e. it's equal to a half, and that's the same for exn as well. Now let's do the intermediate ones, where if we look at the specific example again. We pick a number and we have to compare it to both of its neighbours. Now, imagine that these numbers are set. What is the probability that the middle one is the biggest? Well, there are 3 factorial possible different ways of rearranging these numbers. So, for instance, you could have 2, 3, 4, as we've got there. You could have 2, 4, 3. You could have 3, 2, 4. You could have 3, 4, 2. You could have 4, 2, 3, and you could have 4, 3, 2. So those are all the possible permutations of those. So we've just gone to a number where for every number the number here is set and the numbers beside it are set. But there exist other numbers where all of these permutations are possible, i.e. these numbers are all elements of the sample space as well. So I can put 1, 5, 6 there, 1, 5, 6. These are all elements of the sample space as well. And for any specific one you start with, which was this one, these are all elements as well. So the chance that this one in the centre is actually the biggest is going to be this one plus this one, out of the overall number of them, so it's going to be equal to a third. So the probability of success for all the intermediate ones, so if you think about xi, where I is not equal to 1 or n, 0, 1, the probability that it is a local maximum is a third, and the probability that it's not is 2/3. So the expected value of xi is equal to a third. Okay, therefore, the expected value of our overall thing x, which was counting the number of local maxima throughout the whole permutation, it's equal to the sum of ex1 all the way through ex2 and onwards, plus up to exn. It's going to be equal to a half times 2 for this point and this point, and then plus n minus 2 lots of 1/3. So it's going to be equal to 1 plus n minus 2 over 3, and then we could make that look slightly nicer by rewriting it as n plus 1 over 3 by saying that this is equal to 3 over 3. Okay, so that is the solution to this problem.